Okay, everyone. In case you did not see the announcement, I told your GSIs initially that our next exam was Monday, but I haven't even started grading your last one yet. And I was going to plan the weekend doing so, and I think to make this more manageable and reasonable, I would like to push it off until next Friday the 12th, okay? So if this causes you guys any great hardship, we could always make it for the following Monday. However, I'm going to propose that we have it on Friday for now. Okay, and then if I get an overwhelming response that that's not convenient, we'll have it be the following Monday. I'm sorry, I didn't realize it was going to come up quite so quick, and I still have grading to do. So, all right, we're going to talk about Lecture 14 this week, today. And so that's going to focus on population growth and dynamics, geometric and exponential growth, logistic growth, and population regulation. Okay, so a lot of good stuff. If you guys are interested in ecology, a lot of what we will discuss is basically the basis of ecology, and it involves some mathematical equations, and I don't want anyone to panic because I promise it won't be that bad. Okay, I did not mean to insinuate, by the way, that you guys might not be mathematically inclined. I'm going off of my own personal experience, and to be honest with you, I didn't used to be mathematically gifted or anything. Math was my worst subject when I was growing up, and so whenever I used to see an equation, I would kind of panic because I never really, got along with them all that well. However, I've learned to appreciate them, especially in ecology, and ecology is a lot of math, but we're going to go over it together, and so I promise it will seem like a piece of cake later. There are some errors in this, some conversion errors. So what I would like you to do, because I can't unfortunately control the program, I want you to have the slides, the PowerPoint slides next to you as you go through lecture today, okay? Now, this is a question that you might not be able to answer right now, and that's completely fine, okay? But the idea is by the end of lecture today, we will come back to this question and you should be able to answer it, all right? So go ahead and take a guess now. Just take a shot. Okay, and then when you're ready, go ahead and go to the next slide. The next slide has a video, and it's actually a really cool one to show how human history can make a difference with animals. And then we'll go ahead and apply a couple of these equations as we go through it. Okay, so pause lecture, pick an answer, go to the next slide. If it doesn't load, then what I would do is go to YouTube. It's up there too. Okay, so I hope you guys enjoyed the video, all right? I have to admit, Pablo Escobar, I think this is super cool. I love this example. And so it just kind of shows how hippos, and by the way, I think more hippopotamuses kill people, more hippos kill people than sharks actually do, because these guys have a bad temper. So, grazes all day long, floats around in the water, kind of chubby. I relate to him. I relate to these guys. The hippos, that is. In case you're interested in history, which is something I'm always interested in, Pablo Escobar was a head of the drug cartel, okay, way back in the day, in the 80s and so forth. Now, he died back in 93, and so I think that's before most of you were born. However, believe it or not, at one point in the 90s, he was worth $30 billion, okay? And that was back in the 90s. I think it's like equivalent to $50 billion these days. So one point in time, he was incredibly successful and could afford to have a population of hippos. It's sad that they kind of got left behind, but according to the video and what people have said, these guys are doing just fine. Be interesting to see. Now, when it comes to what can change the size of a population, okay, that's 4 keys to population change. What's that saying is that there are 4 things that can change the size of a population. The birth, or the number of births. Immigration, as in the number of individuals moving into an area. Death, okay, and emigration, the number of individuals moving out of an area. All right, so these are the 4 main contributors to population size changes. So let's look at this in a little more detail, okay? And so this is where we start to add a little bit more math, but once again, it's pretty straightforward. So n sub 1 is just the number of individuals at time 1, okay? N sub 0, that's what you start with, and that should make sense because that's important. B, of course, is births. D is death. I is immigrants minus the emigrants, okay? So this should make sense because it's the n of whatever time is at 1 equals who you started with plus the births minus deaths plus the immigrants minus the emigrants, okay? So this is also known as BIDE, B-I-D-E, birth, immigrants, death, emigrants. These are known as the vital rates of a population. Okay, so let's actually apply this information to our Colombian hippos, okay? And so we want to know how the size of the Colombian hippo population will change over time. So if you start out with 2 hippos in 93, we want to know how many we're going to have by 1997. Now, there's a couple of things I need to tell you about this. First of all, we only count the females, okay? So now we love our male hippos, don't get me wrong. However, the reality is only the females have babies. Okay, and secondly, you need to know that hippos have 1 calf per year, and we're going to ignore the time it takes for those calves to mature. So we're violating a couple of rules, I get that. However, to keep it simple and straightforward and to learn the process, let's go ahead and do that. So what I want you to do now is pause lecture, figure this out, and go ahead and write it down. Okay, you're starting with 2 in 93. How many will they have by 97? Pause lecture, and then once you're ready, start it up again. All right, so hopefully if you worked it out, year 0 you have 2, year 1 you have 4, year 2 you have 8, year 3 you have 16, year 4 you have 32. Okay, yay, I can do math in my head. Sort of. Anyway, that should make sense, right? Okay, that's great. However, let's find an easier way, because if it really starts to get complex really fast, just the thought of it gives me a headache. So let's find a better way. Okay, everyone, so this is another example where you guys need to make sure you get the PowerPoint slides in front of you, because what this should say, and again, it's a conversion issue. I'm sorry, I don't know how to fix it. I'm not that technologically skilled. But what this should read, as you'll see from the PowerPoint, is NT plus 1 is equal to lambda NT, okay? And so what I want you to do now, and again, don't panic, we're going to make this easy. And if you're mathematically inclined, great, good for you. I'm just going by the way I was, okay? So, bear with me. When I used to see an equation, I used to start panicking instantly. So I'm trying to alleviate that, and you guys don't go through what I did. So what I want you to do then is rearrange this equation, okay, and solve for lambda, all right? And so stop the lecture, pause, okay, rearrange the equation and solve for lambda, and then write it down on the slide. And then what you do is you put in a couple of values, okay? So given this particular example, so pause lecture first, solve for lambda. Once you're ready, start lecture again. Okay, so hopefully, all right, if you pause lecture, you would see that NT plus 1 is over N sub T is equal to lambda, right? Easy peasy, piece of cake. Okay, so we know, based on the previous slide, that they have, they started with 2 hippos in 93. That's what N sub T is, okay? N sub T plus 1, we know, if they have 1 calf per year, is going to be 4, okay? And yes, I will give you this information when it comes time to the exam and so forth, so don't panic. Okay, so 4 divided by 2 is going to give you B2. So the lambda for the Colombian hippos is going to be 2. Okay, now you might be asking yourself, where did the 4 come from? Well, we just figured out it a second ago, and I will always give you that type of information. Okay, so just in the previous question, hippos have 1 calf per year. You know that they have 2 hippos, okay? They're starting with 2, so each of them is going to have 1 calf, which is what gives us that 4 divided by 2, which is what makes lambda 2. Hopefully that makes sense. Now, I'm going to give you guys a hint that I wish people had told me a long time ago, is that especially when you're trying to learn equations, and if they're really throwing you, what you can do is write the equation out in a sentence, okay? And I know that sounds crazy, but when you're trying to learn something, okay, and what you need to do is twist it around in your brain so you think of it differently. So N is your number of individuals at the next year, okay, divided by the number of individuals you start with is equal to the geometric population growth rate. Write this out in a sentence. I promise you it will help you remember it. And again, I'm trying to give you guys tips for things I wish people had told me, because as I said, when I first got to calculus and when I first got to real ecology, which involves math, I panicked and no one ever told me that. The other thing to realize too is this is open note, open book. So you guys have the equations. Just make sure you can understand them and that you know what goes where. All right, guys, it's time to apply this again. Remember, it's N n sub t plus 1 is equal to lambda n sub t. If you have 32 hippos in 1 year, how many would there be in the following year? Okay, so you know what lambda is, you know what n sub t is, okay? Take a moment and solve for this. Pause the lecture, okay, stop right here and solve it and find your answer. Okay guys, hopefully on the previous slide you said 64, okay? N2 sub 1 is equal to 2 times 32, that's going to give you 64, okay? So that should make sense. All right, so let's keep applying this. And again, n sub t is equal to lambda, okay? And then lambda superscript t n sub 0. And this connotation is very similar. You know, this should sound familiar. What this is saying is that, you know, n at time t is your population size t. Lambda we know is the geometric growth rate, okay, per individual, per unit time. We know that n sub 0 is your population at time 0. And then t is the amount of time that goes by. So again, look at your PowerPoint slides. See that it's n sub t is equal to lambda superscript t, so lambda at t, and then n sub 0. All right, so what I want you to do is take a moment and pause lecture. Now, it's also flipping things up here a little bit because it's trying to make it more realistic. I will always give you this information, but do not think I'm going to trick you. Again, I'm not, okay? So unless I ask you to solve for lambda or something along those lines, I will make sure that you have enough information to solve this, okay? What we're wanting to do is just gently usher you in, okay, and have you be able to work through this, okay? So what I want you to do again is pause lecture, okay, and then go ahead and solve for this, and then come back and choose the correct answer. So remember, you have 2 hippos at time 0. Lambda is 1.5 because it's more realistic. How many would there be after 4 years? So at t, you're going to put 4. Okay, and so the way you're going to solve for this is n year 4 is equal to 1.5, okay, to the 4th times 2. All right, and so n sub 4 is equal to 5.06, and yes, you guys can have calculators, of course, times 2, okay, is equal to 10.112. Well, you can't really have a 0.112 of a hippo, so choose the next closest answer. At least to my knowledge, you can't have 0.112 of a hippo. So choose the next closest answer, okay? And I promise, also, I will make it obvious like this and not make you guess. But if it happened to have a decimal, but you see a whole number, just pick the whole number, okay? No tricks. The answer to this is C, all right? So this should make sense, I hope. And again, just keep it simple. Write it out. N is the number of individuals at time t is equal to the, geometric population growth rate at time t times the number of individuals that you started with at time 0. Write this out into a sentence. I promise it will help you remember it and be able to apply it. And once again, I don't mean to insinuate that you guys are not good at math because you're Michigan students. You're brilliant. You have to be to get here, okay? It's just I'm putting, I'm remembering what it was like when I was your age, and every time I saw an equation, I generally panicked. I was not good with them. So just bear with me if you're happen to be great at math, all right? The next thing for us to consider when it comes to geometric rate of increase, if your lambda is greater than 1, your population is growing. If lambda is equal to 1, your population is stable, and this should make sense, by the way. If lambda is less than 1, your populations are shrinking. What happens if lambda is 1.047? What does that mean? Take a moment, think about it. We'll talk about it in the next slide. So what does it mean if lambda is equal to 1.047? It means your population is growing, but slowly, okay? So let's recap lambda. Lambda is a geometric growth rate. You can use it to predict one time step into the future. That's where we have the first equation. Once again, it's equal to lambda n sub t. You can also use it to predict several times into the future. And again, n sub t is equal to lambda superscript t n sub 0. Write these down. When you are also writing down the equations in sentences, write the conditions for when you use them, okay? It helps it lock it into your brain and will make you remember it much better. Okay, so apparently in addition to the symbol of lambda, this particular program does not like natural logarithm, okay? So once again, please go download the PowerPoint and make sure that as you're taking notes, these things are correct, okay? So what we're going to talk about with this particular slide is what's known as discrete versus continuous population growth. So when we're talking about lambda, that means it's over a discrete interval of time, like 1 year, 2 years, 3 years, okay? And if you happen to have, animals with a breeding season, like birds and small mammals and so forth, yeah, this can work for them, okay? But realistically speaking, you might want to know at any particular time, instant in time, what the population growth rate is. And so this is symbolized differently and has a different formula. And if you want to know the population growth rate at any particular instant, that's known as R. Okay, and R is known as the per capita growth rate. Write that down. Per capita growth rate equals R. Okay, now we use this when it comes to growing populations, bacteria, okay, humans, all right? So you can switch between R and lambda using these equations, all right? For continuously growing populations, this is the equation that we tend to get. So we basically just substitute. So we have n sub t is equal to n sub 0, and then E superscript RT, all right? And once again, what I want you to do at this very moment is I want you to write out in a sentence what this means, okay? So start with your lambda is equal to E sub R, okay? Write that out. You know what lambda is, you know what R is, you know what E is. It's a constant in math. And so then write out what R is. R is equal to ln of lambda, you know what that is. Therefore, continuously growing populations have this particular equation, okay? And so, again, it's just an equation. Don't let it worry you. You guys have got this, okay? Write it out in a sentence. I'll always make sure you have enough information to address it, but what you do need to know is what goes where and then when to use these equations, because that's going to be part of, what you're tested on. All right, so make sure that all of this stuff makes sense to you, and if not, let us know. Okay, so let's actually draw this out, because as they say, a picture is worth 1,000 words, okay? And so a population's growth rate is the change in the number of individuals of the population, which is known as delta n. That should make sense based on what we're talking about. Per unit of time, that's delta t. Remember, delta just means change, okay? So what I want you to do in the space in this slide is to draw a figure. Okay, so I want you to draw a figure, and I want you to have two axes. I want you to have time on your x-axis, increasing as you go to the right, and I want you to have population size on your y-axis, which increases as you go up. Okay, so think back to math, and go ahead and draw that chart. Now what I want you to do is to draw an exponential growth curve. Okay, and so think back to math. If you're like me, you try to avoid it. Comes back to bite us. And so draw an exponential growth curve. If you don't know what that is, look it up. Okay. And then I want you to draw a line where you connect the two dots. That slope of the line is known as delta n over delta t, which is known as rise over run. Isn't it great when this stuff follows us into other classes? Okay. I promise it's not that bad. All right. And if math whizzes, go for it. Okay. So go ahead. Take a moment, draw this out. When you're ready, go to the next slide. All right, guys, as you drew this out, you should have something like this. Okay, so as we said, number of individuals is increasing, going up the y-axis, time is increasing. As you go to the right, that's the x-axis. So, t sub a is where you start, and then that t is the next time interval. And then, so that's delta t, difference in time, difference in individuals. The slope is delta n divided by delta t, rise over run, okay? And so the slope of this line is going to be delta n over delta t at where time is equal to a. All right, so hopefully this looks familiar, okay? What I want you to do is to think through this then and think, what would the values, we know what the lambda values are, okay? So what would the values have to be for R then, given what we're sort of talking about here? So what would indicate a population growth? what would indicate stasis, what would indicate decreasing, okay, if you consider R with respect to lambda. Okay, guys, so given what we've talked about, let's actually fill this out. Okay, so populations are growing, as we said, when lambda is greater than 1. R, by the way, has to be greater than 0. So switch out the equals and put it greater than 0. Okay, populations are stable when lambda is equal to 1 or R is equal to 0. Okay, and then last but not least, populations are shrinking when lambda is less than 1 or R is less than 0. Okay, and so make sure that this makes sense to you because it tells you about the population dynamics and then allows you to answer questions about certain populations like the one you're going to see on the next slide. All right, guys, so given what we talked about a second ago, okay, so for the Colombian hippos, R is what? And then lambda is what? You guys have the information. You could actually go back and calculate this if you wanted to. But for the purpose of this question, at this point, all I'm asking you is to choose between A, B, C, D, or E. Okay, and so pause for a moment, address this question, and when you're ready, start it up again. Okay, so the answer, by the way, should be A. Okay, so if that doesn't make sense, definitely let me know. But R is going to be greater than 0 because your population is growing, and lambda is going to be greater than 1 because, once again, your population is growing, as we know. Okay, so what I want you guys to remember is that you can make any rate a per capita rate. All you have to do is divide by the population size of n. Okay, so you can switch birth rate to per capita where it's B divided by n, death rate D divided by n, and so forth. Okay, and what that gives you is R is equal to per capita B plus I plus D, or I'm sorry, minus D minus E. Remember and notice the change in notation. When it's per capita, it's small letters. When it's not, it's large letters. Okay, there's a difference. Under optimal conditions, when B is as high as possible, so you have as many births as possible, and you have as low number of deaths as possible, R is going to reach what's called a maximum value, and this is known as the intrinsic rate of increase, otherwise known as R max. Okay, and so when this happens, you have dn dt is equal to R max times n sub t. Once again, write this out in sentence form. And all this is saying is that your population is increasing as much as possible because you're adding individuals and not that many individuals are dying. Okay, so let's break this apart a little bit. Okay, so considering our exponential growth of Colombian hippos, we have the total number of hippos per year. All right, what I want you to do then is fill out the right side of this column, and you're going to consider the number of hippos added starting at year 0. Okay, so pause lecture, fill this out. Remember, at year 0, how many did you add? You didn't add any. Okay, it wasn't until year 1 that you started adding them. And fill out the right side of this column. If all went well, year 0 you had none. Year 1 you added 2, year 2 4, year 3 is 8, 4 is 16, 5 is 32, 6 is 64, year 7 is 128. So you can say that the hippos are growing exponentially. But what I want you to consider is R or lambda, they stay constant. Okay, your growth rate hasn't changed. They're doubling each time. So the population's growing, but the number that's added per year is increasing because your population size is increasing. But those growth rates, those are constant. Okay, and make sure that that makes sense because that's actually really important as we keep going. So let's actually apply this. Okay, so you're in charge of cleaning up an oil spill. You have a microbe that breaks down the oil, and by the way, we actually have these. Yay! Makes me happy because we obviously seem to mess up the environment enough as it is. You do have limited resources, and that's real life, okay? And so you can either do A, B, or C, and don't choose C. Okay, so which strategy is going to result in a faster cleanup? Don't pick C. So choose between A and B, and then once you're ready, go to the next slide. So if you guys are in charge of cleaning up this oil spill, okay, these are the two different choices that you could come to. So on the left, if in fact you doubled the population size of who you started with, you'd only have 4.5 million bacteria. If you doubled the growth rate, you would have 50 billion. Okay, so basically growth rate makes a huge deal in population size, and as you can see, it's illustrated here. So let's talk about hippos and some general hippo knowledge, okay, because these guys are pretty interesting. So their scientific name is Hippopotamus amphibius. This means they can live on land or water. They're found through sub-Saharan Africa. Unfortunately, they are considered threatened. There's been a population decline in the past decade due to exploitation. If you happen to be curious, they can weigh up to over 7,000 pounds. They have a high blubber content, so they float. I said I feel akin to them because they eat a lot, they float around in water, and they're a little grumpy. Okay, so I will tell you a brief story with regards to being able to float. I don't know if you guys have ever gone scuba diving before. I went scuba diving with one of my cousins back when I was really young, and I will admit I absolutely loved it. My problem was I floated way too well, and it took every ounce of strength I had to keep myself underwater. Needless to say, I'm not in danger of drowning anytime soon. But the funniest part was the next day, I didn't realize how much I was fighting to stay underwater until I literally couldn't move. Every muscle in my body hurt. So I float much better. So what these guys also do, which is interesting, is, and I don't, the hippos do, they release a pink slime that has sunscreen properties. The nostrils are on top of the snout. That lets them still breathe while they're totally submerged. They eat plants. They scavenge on carcasses. They're not super picky, but again, they lead a pretty good life where they're at. Now, my husband just chimed in and reminded me that I do float very well. I'm going to ignore that comment. Anyway, back to the hippos. So, believe it or not, there are little critters that actually live in the rectum of hippos. Okay, and these are known as rectal leeches. And before everybody goes, ew, yes, ew, nature's gross. Okay, I hate to tell you, but it's true. So you might ask yourself, why on earth would one organism want to live in the butt of another organism? Well, okay, ew, but they can get some good resources there. Okay, so the thing to consider is that leeches are animals. Okay, and so they're multicellular, they're eukaryotes, they have a gastrulus stage, they produce collagen proteins, okay. In addition to that, you should know that they're hermaphrodites, so they have functioning male and female sex organs simultaneously. They produce male and female gametes and they do not self-fertilize in most cases. Okay, so I will include a link in case you guys are interested. However, these guys definitely can eke out a living where they're found. One we may not consider desirable, but it works for them. Now that we've shared that fun fact of rectal leeches, which I do promise we will use in the next couple of slides. I don't know about all of you, but I had a lot of friends in college that were not bio majors. My husband is not a scientist either. I thoroughly enjoy sharing this information with them, whether they want to know it or not. Don't even get me started on microbes, what I've tortured my daughter with. But anyway, so let's continue using lambda of 2 for our Colombian hippos. How many hippos would there be after 20 years? Pause lecture and solve for this. Remember, we started with 2 in 93. T is equal to 20. So considering this information and plugging the information in, you would get approximately 2 million. Okay, so will we actually have 2 million hippos? No, absolutely not. There are things that limit population growth, and especially with any animal, resources are going to be one of the things that actually limits the population and keeps it from growing indefinitely. And what we're concerned about, by the way, as humans, is we want to make sure this doesn't happen to us. Okay, we'll keep going and come back to that later. So the question of, will Colombia be overrun by hippos? The answer is no, okay? So the thing about nature is you can't keep growing exponentially indefinitely. It's not going to happen. The way nature works, as we all know, is that resource limitations will stop exponential growth rates. What might limit this? Not enough food, space, nutrients, breeding sites, too many rectal leeches, okay? Too many parasites. If you get a parasite overload, then things don't go well. So eventually, the limit of resources is what's going to stop slow the population growth. Okay, so if our population growth is limited, and so, you're growing and growing and growing, and then all of a sudden you start running out of things, what change do you expect in B as your population size increases? And then what change do you expect in D? And then what effect should this have on R? Take a moment, pause lecture, address this, and then keep going. What you would expect is that the birth rate should decrease. The death rate should increase, okay? And then R is going to slow down. All right, and so that should make sense, because as you start hitting the maximum of with regards to resources that an area can hold, the population is not going to just keep growing happily. Things have to slow down, all right? What this means is we are hitting what's known as carrying capacity, okay? And by the way, that's represented by a capital K, okay? So we're starting to talk about now, we're shifting into what's known as density-dependent growth, okay? Otherwise known as logistic growth. Write that down. Density-dependent or logistic growth. So what this means, and you need to write this down too, is that the number of new individuals added to the population will decrease as your population size increases. So the number of new individuals added to the population will decrease as your population size increases. And this should make sense, okay? So as space and resources are used up, your growth is going to slow down, especially once you hit carrying capacity. Okay, and carrying capacity is basically set based on how many resources are there. And so carrying capacity is one value where a population can come to equilibrium. Okay, and so one of the regulating factors is competition, and this should make sense. So carrying capacity is set by what's known as intra-specific competition, so within species competition. Excuse the barking dog, speaking of within species competition. So carrying capacity is set by intra-specific competition, and we'll learn more about inter-specific competition later on. Okay, so they can regulate population size, but they don't really influence the carrying capacity. So make sure that this makes sense. And the carrying capacity for this population, if you were to draw a line, okay, starting with, and you're going to draw a horizontal line, where do you think carrying capacity would be? Well, it's going to be a little bit above 500, okay, because that's about the number of individuals that can be supported at this particular location, okay? So, yeah, hopefully that makes sense. Okay, so the first thing you do when you see a graph, which I wanted you to do on the previous slide too, I forgot to mention it, is that you read the axes. And the thing to pay attention to is the axes on this graph are different than the last graph, okay? Now, we're still talking about logistic growth, all right? But what happens is, so on these axes, you've got density, which increases as you go to the right, and that's on the x-axis. And on the y-axis, you have population growth rate, which increases as you go up, okay? And what I want you to pay attention to is the line, because what it shows is that R decreases as density increases. That should make sense. Your growth rate, your population growth rate, little r, is going to slow down the more individuals you have in your population. Okay? So the other thing to pay attention to, just so you know, is that the x-axis is not really a log scale. The vertical lines are unevenly spaced. Don't let this panic you. Just read the axis. It's fine. Okay? And realize that as population size increases, R decreases. And this is actual data for Daphnia, which are tiny little water fleas. So incredibly cool little creatures. I think there's a couple of labs that work on those around Michigan. Very interesting little guys. Okay, so let's apply this and go in a little bit more depth. And oh, look, more symbols that look weird. Okay, so please pull out your PowerPoint slide. Okay, and what I want you to know from this particular slide, first of all, population size is on the y-axis. Okay, time is on the x-axis. This should look familiar, and you have an early growth is rapid as you start out, but then it begins to slow, okay, and later the growth falls to 0. And apparently the equation for this model in your textbook is wrong. Use the model you have here, okay? And so what happens is we're just going to add the carrying capacity into our exponential growth model, okay? And once you do that, it gives us a logistic growth model. And I'm hoping these terms make sense. So dn over dt, write it out in a sentence, define every term first, and then write out in a sentence what this is equal to R max. We've talked about that, okay? Times n sub t, you know what that is. And then in parentheses, it's carrying capacity minus the number that you started with divided by carrying capacity, all right? The other thing I want you to pay attention to is that the higher carrying capacity is, and the lower n is the number that you started with, your population's going to grow, okay? But if you have a lower carrying capacity and you have a high n, and it's divided by carrying capacity, your population's not going to grow much because there's really no room. Make sure that that makes sense to you, okay? And once again, I want you to write out what every single term of these is, and then write it out in a sentence and make sure it makes sense to you. All right, guys, so exponential versus logistic growth. Again, I'm sorry, the symbols, I don't know how to fix that, but just use your PowerPoint slide for this anyway. So I just said this. Now I want you to address it. Okay, so if n is very small, close to 0, what does the term in parentheses come? If n is very large, close to k, what does the term in parentheses come? What I want you to add to this is what does it mean for the population growth? Is it going to grow much? Is it not going to grow much? Think through that, okay? And given what we've talked about, this should be easy. Okay, guys, so we have our 2 lines plotted out based on our equations. Once again, we see a graph. You read the axes. Population growth on Y, number of generations on X. So they both increase as they go up and to the right. So what I want you to do is look at these 2 equations. dn over dt equals 1.0 times n. dn over dt is, that's for, the first one I said was for exponential growth. The other one is for logistic growth. What's the difference between the 2? Look at the equations. Know what the difference is. It's adding the carrying capacity. Okay, so that part, that carrying capacity, will decrease as your population numbers get closer to that value, all right? And when multiplied by R max, that will give us the real or observed R, okay? So all that's different here, again, is the fact that one of them incorporates carrying capacity. Now here's another question for you. Which one is most likely to happen in nature? Exponential growth or logistic growth? This should be super easy. Obviously logistic growth. Okay, so exponential growth can't go on forever. To be perfectly honest with you, what scientists are worried about is that humans are currently in the exponential growth phase. Okay, so we haven't hit carrying capacity yet. Do you think we ever will? And what do you think will happen to us? Don't everybody panic. Technology adds a lot to this, okay? But this is kind of what researchers are thinking about because we've not hit our carrying capacity. Can technology help us surpass that? Do we need to go settle other planets? Who knows? By then I'll be dead and you guys have to deal with this. Sorry, I couldn't resist. Anyway, so just what I want you to get from this is what the 2 different lines look like when you do and don't have carrying capacity in there. Okay, so something that y'all may have noticed earlier is that I told you that R should decrease as resources become limiting. However, on the previous 3 slides, I've told you that R max should stay constant, and it's actually the carrying capacity that slows down population growth, okay? So you might want to know how to sort of reconcile these things, especially if that you happen to notice that. So what I want you to consider is that R is basically the actual instantaneous rate of change in the population, and it's almost always different than R max. Okay, so R max is the maximum increase of a population. But the reality is that R is based on measured or observed values. It's based on the vital rates, and R max is not. Okay, so don't panic. Just realize that there's a difference between the 2 most of the time, and that should make sense since R R depends on the birth minus death plus immigrants minus emigrants, and R max is just if the maximum rate, and that of course is going to be different than what's really going on. So you might be asking yourself, well, what happens if population size exceeds carrying capacity? So in other words, N is greater than K. And I would say, aha, that is an excellent question. Okay, so experiments have actually been conducted to test this, and they found that populations that where this happens to, they'll typically overshoot carrying capacity and then they'll stabilize. Okay, so basically what happens is they overshoot, but then they have to shrink and get back down to carrying capacity. Now again, what we're hoping is that this doesn't happen with humans. Nobody wants a huge death rate, death toll, any of those. Knowing my luck, I'd be the first to go, okay? So natural selection should have taken me out a long time ago. So, hopefully humans we'll be able to have technology to make sure this doesn't happen to us. So y'all keep your fingers crossed and, go science. Let's hope this happens and works. And when I say I hope this happens, I mean science helps us figure a way out of this. All right, so we need to consider what influences population size. Okay, and so when it comes, there are two different types of components. One is known as biotic and the other is abiotic. Okay, so all of these factors can change population size, but realistically speaking, only the biotic ones can regulate it. Okay, and so of the biotic factors, only those that add a negative feedback, in other words, not a mutualism, are going to make the biggest difference. So predation, competition, parasitism. Okay, so my daughter has been traveling and she's supposed to come back next week, and my husband and I lovingly call her our little parasite. Because she takes away all of our resources. Anyway, she looks at it as a mutualism. I beg to differ. Okay, those are all biotic. That means it's with a living thing. Abiotic, those are things like temperature, disturbance, precipitation, pollution, salinity, pH, and all sorts of other good things. They will influence a population size. Okay, they can all change it in one way or another. So when we talk about regulation needs a negative feedback, this is what we mean. Okay, and what you can do is you can think about this like a thermostat. Now, I don't know about all of you, but in my house, we have thermostat wars. Okay. My daughter likes it hotter in the winter than I do and cooler in the summer than I do because she doesn't pay the bills. And my husband and I also argue about that. Okay. But if you think of a thermostat, when the temperature is too cool, the heat will come on. Okay. But then when the temperature is too warm, the heat will turn off. Well, you can think of a population, and that set point is going to be the carrying capacity. So let's say they happen to overshoot too much food, something along those lines, few predators, and they overshoot the carrying capacity, but then they run out of food, so then they end up falling below carrying capacity. But then because they're below carrying capacity, there's more food, and let's say less predators and so forth, so then they start overshooting again. So there's a little bit of wiggle room. Okay, but basically everything kind of sticks around that one set value dash line. And again, that's going to be the carrying capacity. Okay, guys, so it's time for us to apply this. Okay, so which of these lines shows density dependence and which one shows density independence? First thing you do when you see a graph is you read the axis and you figure out what's going where. It is not answer C. Okay, stop lecture, take a moment, address this question. Choose the right answer. When you're ready, start up again. And if everything went well, you chose A, and that should make sense. If not, let me know. Okay, guys, let's show how this stuff actually is important and why it makes a difference with real science, okay? So as you can see here, we have a real experiment, and by the way, this is in Meg Duffy's lab. And so they do experiments on indoor what are called mesocosms, and that's at the bottom right. Now, what I'd like you to notice in this case is a mesocosm is basically a fancy word for 5-gallon paint buckets from Home Depot. Okay. They finished one of these experiments not too long ago, and they estimated that carrying capacity for the mesocosms is about 100 animals per liter. Okay, so let's apply this information. If you start a mesocosm of 10 for one of your buckets, 100 for another one, and 200 for another one, what would you expect the initial instantaneous population growth rate to be? Okay, so that dotted line, by the way, represents 0. Okay, so what I also want you to think of too, I said a single bucket, but realistically speaking, if you're running an experiment, there's going to be multiple replicates per treatment. Okay, so where should your values be if you're starting out with only 10 animals okay, versus 100 animals versus 200 animals with regards to R, keeping in mind that the dotted line is a 0. Pause lecture. Go ahead and answer this, okay? So what I'm wanting you to do is be able to think through this. If you have 10 individuals, then it's not close to the carrying capacity, because remember we said that's 100, in which case R should be clearly above 0 for 10. Okay, if it's 100, then that's at carrying capacity, and that should overlap with 0. Okay, if it's 200, then you've got too many individuals, and your population is going to shrink, so R is going to be less than 0. And again, this isn't just some abstract concept. We're actually talking about real science, and that's actually super cool. So what you guys could have had on the previous graph, by the way, is to use a bar graph as long as 10 was above 0, 100 was at 0, 200 was below 0. You can also use an X to say where you thought the values would fall. It's entirely up to you, okay? Let's just go one step further. We're going to ignore the squeaky guinea pigs we can hear in the background. And I want you to consider in each of these situations, what would the birth rates look like and what would the death rates look like? Once again, assuming, draw your dotted line, okay, keep it in the same spot, realizing that K carrying capacity is 100, okay? You're also going to assume these are closed, so no immigration or emigration. Let's keep it simple, all right? Pause lecture, take a moment. You can use X's, you can use bar graphs, just distinguish between birth rate and death rate, and figure out where they would be for 10 animals versus 100 animals versus 200 animals. Pause lecture here. So if you have 10 animals, your birth rate should be high, your death rate should be low, okay? If you're at 100 animals, your birth rate should be, as you hit close to 100, your birth rate should be equal to the death rate. At 200, once you approach your over-carrying capacity, in which case your birth rate should be the lowest and your death rate should be the highest because your population is going to die off. Okay? Again, I'm just wanting you to apply things that we've talked about to the actual real science, so this doesn't have to stay as something, that seems, well, not as interesting as it really is. Okay, guys, so that is the end of lecture, and I just inserted this slide because I thought of a bonus extra credit I'd like you guys to do. So in the very beginning of lecture, you were asked a question. Now I want you to answer it, okay? That's not the only way to get the extra credit, though. In addition to that, what I want you to do is write out the equations and then show me what each of the symbols or those letters mean, and then write it out in a sentence. If you guys do that, which is going to help you study for the exam, and you will thank me if you take general ecology. Trust me, this will make your life much easier. If you guys submit that, I will give you an extra credit point, okay? And so I'll make it due for Monday evening. I think that's fair. All right, so you guys stay safe. Have a wonderful weekend. I'm also going to give you some additional materials just because of the fact that a lot of times the first time you see these things, it's nice to see it from multiple sources, and there's a ton of really good resources out there for you guys, so I'm going to list it in the announcements. I highly encourage you to check them out, okay, and make sure that everything makes sense to you. If you have any questions, definitely send me an email. I will hold office hours again on Monday, and I'll send out the Zoom as soon as I get done here. Have a great weekend, everybody.